if you're subtracting, you just subtract the means. So for means, you do kind of what you thought you would do. For variances, we need to know that these two are independent of each other in order to do this. Most of the time, if they're asking you to combine random variables, they will tell you that they are independent. Okay? If they don't tell you they're independent, go ahead and do it. But it would be wise to write down, we're not told they're independent, but here's what I would do if they were. But I don't remember ever seeing one where they don't tell you. So, okay, so when you add random variables and you're trying to combine the variance, you just do the variance of x plus the variance of y. And that gives you the variance of the combined variables. So when you are subtracting, you do variance of x plus variance of y.
Wait, you subtract, you add?
Yes. So variances always add. Regardless of if you're adding or subtracting the means, you still add because you're getting more varied information when you're combining two variables. Okay? So you're increasing the variance because you're combining another data set with your previous data set, so it's getting larger variance. So this is one you have to be careful because you get going along with it and you go, oh, I'm subtracting, so I subtract. But variance is always add. So you want to make sure you remember that. For standard deviation. So for standard deviation for two random variables, whether you're adding or subtracting, first you want to find the variance. Then take the square root. So sometimes they will give you the standard deviations and ask you what is the combined standard deviation. You have to convert them to variance, add them together, then take the square root. And we'll look at some examples of this, so hopefully it'll make sense. Normality. You remember z-scores, a normal model, all of that stuff's going to come back in here. So if each of the random variables has an approximately normal distribution, then the combined variable will also follow a normal model. So that means if they want you to find a probability, you just use z-scores. So all of those things that we learned for normal models comes back into play here. You go to the front page, get those filled in. All right, let's look at some examples. So example number 1. This is an AP exam question. And this gives us information about 4 runners on the new high school team. And it says this team is planning to participate in a race in which each runner runs a mile. The team time is the sum of the individual times for the 4 runners. Assume the individual times of the 4 runners are all independent of each other. There's that independence. And individual times in minutes of the runners in similar races are approximately normally distributed with the following means and standard deviations. So, the first part, it says runner 3, so this one right here, thinks he can run a mile in less than 4.2 minutes in the next race. Is this likely to happen? So we're just wanting to know what is the probability that runner 3 can run the mile in less than 4.2 minutes. So all of those things that you needed to include before, you still need to include. You need a sketch, you need to to show your work, and you need an answer in context, just like you did before. So if we draw a sketch, we want to label the mean. So for runner 3, the mean is 4.5. And they think you can run it in less than 4.2. So we want to label the 4.2. It's going to be over here. 4.2. And he thinks he can run it in less than 4.2 minutes. So we're going to shade to the left, because that's where it's less. So there's our sketch. We need to find our z-score. So we need to plug the values in to get our z-score. So z-score is the value that we're looking at, 4.2, minus the mean, which for runner 3 is 4.5, divided by standard deviation, which is 0.14. So on the z-score table, it only goes to 2 decimal places for z-scores, so we always round it to 2 decimal places. So we want the probability of the time being less than 4.2. So we're looking on the z-score table at negative 2.14, and we want shaded to the left, which is what we have and what is on the table. So we're just looking at that value. So 2.14 would be right here, 0.0162. Found the probability, I need to write an answer in context. So I'm going to go back and just rewrite the way the problem was worded. So the probability of runner 3 completing the mile in less than 4.2 minutes is 0.0162, and we're going to say that is unlikely. It's very unlikely this person is going to run the mile in less than 4.2 minutes. You guys remembering doing this now? It's been a little while since we've done it, but just take quite a bit of time on some scores and probabilities. Okay, so part B says the distribution of possible team times is approximately normal. What are the mean and standard deviation of this distribution? So now we're looking at, instead of individual runners, we're looking at the entire team combined. So if we want to know the mean for the entire team, we just have to add together the means for each runner. And we want to show that's what we're doing. So we'll show that it's 4.9 plus 4.7 plus 4.5 plus 4.8. We're going to show what we're adding to get to our new mean. So 18.9 minutes. So that would be the mean time for this team of 4 runners. For standard deviation, remember we want to combine variances. So we were given standard deviation. So to get the variance for each of these, what do I need to do with those numbers? Got to square them. Okay? So I'm going to say this is 0.15 squared plus 0.16 squared, and so on. And then And to get standard deviation, I just take the square root of all that. Any questions on that part, and how to get mean and standard deviation from a list of information? Okay. So part C says, as a team, the best relay time they have recorded so far is 18.4 minutes. Okay. Using the mean and standard deviation up here, what is the probability the team will beat its best time in the next race? So we're going to use this mean, this standard deviation, with this 18.4. So to draw a picture of it, we label the mean in the middle as 18.9. 18.4 is going to be somewhere over here. And we want it to beat the time, so less than that amount of time. So we use this information, find a z-score. So z equals the value that we're looking at, so 18.4 minus the mean, 18.9, divided by standard deviation, 0.3003. Go to my table, and I'm showing a value less than, so that's what's going to be on the table. I don't have to subtract from 1 or anything. So I want the probability of getting a value less than 18.4. So there's negative 1.67.0475. Then there's my context for how I'm going to write this out. So I'm just going to write that same statement is, and then give this probability. How do you feel with that one? Questions? Do you guys feel okay with it? Just combining this with stuff that we've done before. All right, let's look at example 2. Example 2 says, Hoop Fever is an arcade basketball game in which a player has 60 seconds to make as many baskets as possible. Morgan and Tim played head-to-head every Tuesday. Let M equal the number of baskets made by Morgan and T equal the number of baskets made by Tim in a randomly selected match. Based on previous matches, we know that for Morgan, the mean for Morgan is 39.8 and with a standard deviation of 5.7. And for Tim, the mean for Tim is 31.2 with a standard deviation of 10.3. So, they want to know, for this first part, how many more baskets can Morgan expect to make? So, what we're looking at is the mean for Morgan minus 10. So we're looking at what is the difference between the two, expecting Morgan to have more. So this will be the mean for Morgan, 39.8, minus the mean for Tim, which is 31.2. Should be this 8.6 baskets. Then to find standard deviation for Morgan minus 10, we have to convert the standard deviations to variance, combine them, and then take the square root to get back to standard deviation. So, Morgan's is 5.7. I'm going to square that to get his variance. Tim's is 10.3. I'm going to square that to get his variance. Now, if we're subtracting, what operation do I need to do with these variants? Add. Very good. And then I will take the square root to get back to standard deviation. So you can think of this as kind of like, they call this the Pythagorean theorem of statistics, because you square them, you add them, you take the square root, kind of like when you're doing Pythagorean theorem. So this gives me 11.7720 baskets. Okay, so part B says, you'll notice you were asked to calculate M minus T. So if M minus T is 0, what does that mean? What happened if we get 0? Think about the context of this situation. M is the number of shots made by Morgan. T is the number of shots made by Tim. So if we get 0, what does that mean happened? There you go. So 0 represents a tie, basically. Both scored the same. So both made the same number of baskets. What does a positive value represent? Yeah, Morgan scored more than Tim. Negative represent. Morgan scored less than Tim, or Tim scored more than Morgan, whichever way you want to write that. again, this example is another one straight from an AP test. So just realize sometimes they ask you to understand what something means in context without doing a calculation with it really. So you need to be aware of it. Okay, part C says assuming the number of baskets made by both Morgan and Tim follow an approximately normal distribution, find the probability that Tim will make more baskets than Morgan in a randomly selected match. So that means, am I going to be getting a positive score, a negative score, or 0? If I'm thinking Tim makes more than Morgan. Negative. Okay? So we're going to say that Morgan scored less than Tim. So we're looking for a negative value. So what that looks like when I draw the sketch, I found up here in part A that the difference between the two has an average of 8.6. So that's going to be here in the middle. And I want to know, when is it a negative difference? So I'm going to be looking at labeling 0, and I'm looking for where is it negative. So I'm going over here. Does this make sense to you, that that's the area that we're looking at? Okay. So then we're just going to find a z-score. So 0 minus 8.6 over our standard deviation for the combined, which we found up here in part A was the 11.7720. So I'm going to look this up on my z-score table, z-score of negative 0.73, and since I'm looking for an area to the left, I don't have to do 1 minus, so I'm just going to get 0.2327. So right here is my probability context. I'm going to use that to write my context statement. Still doing okay with this? Okay. So, part D. What is the probability that Morgan will make at least 35 more baskets than Tim in a randomly selected game? So now we're saying when we do this Morgan minus 10, we're going to get at least 35. Okay. So this one, we still have a mean of 8.6. But we're now saying he's going to score more than 35 more baskets than 10. So we need to find a z-score. probability of getting more than 35. On our table, it's going to tell us less than. So now I do need to do the 1 minus whatever I get on the table. So 0.9875. To write my context, I'm just using the statement right out of the question. Okay, so these notes are going to go on page 23 in your notebook. So go ahead and attach those in there if you haven't already. Do in this, and then we'll go over it.